Hi there, this is Mohammed Aqeeb, and today I am going to be teaching about acidic order as my demo topic. All right, so this particular topic has been chosen randomly, and I am able to teach organic, inorganic, and physical chemistry as I have masters in chemistry. So I am comfortable in all of the three disciplines. So just for the sake of demo lecture, I have chosen this basic topic, and now we are going to go ahead with this one. All right. So now we have four given compounds over here. Okay. So first one is orthofluorophenol, second one is metafluorophenol, third one is parafluorophenol, and the fourth one is just phenol. Okay, so all of these, as we can see, all of these structures have been attached with a fluorine atom, a fluoride group over here. Okay, and this one doesn't have any side atom attached to it. And now what we are going to do is we are going to find out which one is most acidic and what is the order of acidity among these four compounds. All right. So before we begin with this one, let me tell you about the concept which is behind this order of acidity. Okay, so uh, there has to be some establishment, right? There has to be some basic idea from which we can compare the acidity of these four compounds, right? So that governing factor is inductive effect. Okay, so there are other effects as well, mesomeric and hyperconjugation, but when it comes to halogen, the inductive effect is the most dominant among them. Okay, so right now, for the sake of this particular demo topic, we are going to only talk about inductive effect. Okay, so let me just brief you about what exactly inductive effect is about. Okay, let me just go ahead and write that over here, which is inductive effect. Okay, now so let me tell you about what exactly is inductive effect. I think the F has gone far away. All right. So inductive effect, it is basically dependent upon the electronegativity difference of the atoms. Okay. So what exactly is this electronegativity? Okay. So electronegativity is basically a force of pulling of electron. Okay, so when an atom is highly electronegative, it is going to pull the electron from the other atoms, right? In the chain or in the carbon chain or in the compound, in the ring. Okay, so the electronegative atoms are going to pull the electrons from the compounds which they are attached to. All right. And as we know, the fluorine is the most negative atom among all of the elements in the periodic table till now. Okay. So this has the highest tendency of pulling of electron from the carbon chain. All right. So now we have this basic idea about electronegativity. Now, second point is this inductive effect is distance dependent. Okay. So it is distance dependent, meaning that the electronegativity effect is going to depend upon the distance between the atoms, okay, and the electron drawing group over here. Okay, now we are going to see the application of that in this particular example, how distance is affecting the acidity of these molecules. Okay, so another point about this one is that it is a permanent effect. Okay, so it is not a temporary sort of a effect. It is a permanent effect. Okay, so it is going to exist in the molecule and it is not going to vanish. Okay, it is not going to go away. All right. So now we have these basic idea about inductive effect. All right. So after this basic introduction about inductive effect, what I'm going to tell you is why exactly are we talking about this electronegativity difference? Okay, we just want to find out the acidity, right? So we can just remove the hydrogen and then yeah, we can say this is getting removed from here, from here, from here. But the question is, how are we going to determine that which one is more acidic, right? There has to be some rate of acidity. So what happens when something is acidic? Okay, it loses hydrogen, right? So it loses hydrogen. So as we know, oxygen is also another electronegative atom. Okay. So let's say this is a OH bond over here. Now the electron of the this particular covalent bond is going to be pulled towards the oxygen. Why I'm saying that? Because oxygen is also electronegative, right? So all of the electron density is going to be pulled towards the oxygen. And when the hydrogen leaves, okay, it is going to be losing its electron which it shared while making this particular covalent bond. Okay, so this is going to be H plus. And as this is H plus, this is going to be H minus. There's going to be a electron cloud, electron density being created at the oxygen molecule. I'm sorry, oxygen atom. Okay. Now this has the electron density. So what is going to happen now? Now, when there's electron density over here, so this particular molecule with oxygen having electron density and it is being attached to a benzene ring, it is called as a phenoxide ion. Okay. Now, what is going to happen over here? The electron density. We are supposed to do what you're supposed to do is we are supposed to stabilize this electron density because electron cloud is very much high over here and oxygen will not be able to handle this much electron density. Okay, so there has to be some factor or some other external influence which will help oxygen to stabilize this electronic charge. Okay, so for that purpose, when we attach a fluorine, let's say over here, okay, so as we know, fluorine is very high electronegative, very highly electronegative. So what it is going to do is it is going to pull the electron from the benzene ring over here. Okay, so it is going to pull the electron over here. So as it pulls the electron from benzene ring, so over here at this position, there is going to be a lack of electron because carbon makes four bonds, right? And the electron is going to be pulled away from it towards the fluorine. So the electron is going to be the electron in the bonds is going to be lost or it is going to be decreased. So electron density is going to be decreased over here at this particular carbon. So what is going to happen now is this electron density at oxygen is going to be transferred to this bond over here. Okay, so now there is going to be a conjugation or the transfer of electron cloud from oxygen to this bond over here. And now this is how it is going to stabilize the electron cloud over here. Okay, so now as we know over here that fluorine is removing or pulling the electron from the benzene ring or the system as a whole. Okay, and the electron cloud of oxygen is being used to stabilize this electron density decrease or electron scarcity. Okay, so now, as we have established few facts about inductive effect, minus I effect, is we are it is a distance dependent effect, right? So as we see over here in the orthofluorophenol, it is at the ortho position. What exactly is ortho position? It is the first position which is attached to the functional group. So functional group is OH group over here, and the first position is this one and this one. So both of these position can be called as ortho positions. Okay, and over here the second position from this side and from this side, these two positions will be called as meta position, and this one, the far away position from first carbon, it is going to be called as the para position. Okay, so that's how the name is written: orthofluorophenol, metafluorophenol, parafluorophenol, and just phenol over here. Okay, so when the hydrogen leaves, the pulling of electron, the effect of electronegativity, the inductive effect of fluorine is going to be very much higher in this case. So it is going to be very easy for this molecule or this compound to get stabilized, right? To stabilize its electron density. Now, when it comes to metafluorophenol, as we know, the fluorine is little bit far away from the functional group over here. So it is going to be little bit harder, or yeah, a little bit less effective, but it is going to pull the electron as it has very high electronegativity. So it is going to pull the electron from here, and it is going to stabilize the oxygen electron cloud. And comparatively, when we go to the parafluorophenol, it is going to remove, or it is going to pull the electron from the benzene ring, right? It is going to stabilize the electron cloud, but relatively very less as compared to orthofluorophenol. And this one over here, it doesn't have any electron withdrawing group or any electronegative atom attached to it, so it won't be able to stabilize as as compared to these three compounds. So now we have understood that based upon the stability of the phenoxide ion, this is going to be the most acidic. Then metafluorophenol is going to be the next one, then parafluorophenol, and then phenol is going to be the least acidic. Okay, so this is the acidic order of these atoms. I'm sorry, these compounds. All right. So this was my little topic for the demo. Okay, I hope you have understood this concept, and I hope I was able to convey the concept behind the arrangement of the acidic order. Okay. All right. Hoping to hear from you. Thank you so much. Bye bye.